just a quick little review on rates, reaction rates. So a rate is change in quantity divided by change in time, which we abbreviate delta Q over delta T. A lot of different things that we can use to measure the change in quantity. So it could be how the temperature changes over time. It could be the color change, the pressure. These are all depending on what sort of system you're measuring. The mass of the system, and tied to pressure, you could also just do volume of gas produced, etc. There's many things. So what would affect the rate? Well, the easiest thing is increasing the concentration of the reactants. If you increase the concentration of the reactants, you will increase the rate of the reaction due to more collisions. If you increase the temperature, you get an increased reaction rate, and we said it approximately doubles every 10 degrees Celsius. We get surface area. If you increase the surface area, then you get an increase in rate. Increase the rate of the reaction because you're getting more collisions. But this is only really applicable to heterogeneous reactions. And what I mean by that is, like, if you have a solid metal reacting with some aqueous solution or water or whatever, and if you divide up the metal into smaller chunks, you're getting more of a surface area. Whereas if you had just aqueous, so NaCl aqueous plus, I don't know, potassium nitrate aqueous, you can't increase the surface area of an aqueous solution. So that's when you go to mixture. The nature of the reactants, when we say that, that's kind of a catch-all phrase. That's going to be the geometry of the molecules. So a sodium ion, one little ion, it's easier to have a proper collision versus some complex organic molecule like that. That's also going to give us, or be tied to the reactivity of the molecule, which can be tied to electronegativity. Things like that. Things you don't have any control over. Just it's how the molecule is. And also that ties into this nature of the reactants. Number of molecules reacting. So for example, sodium and Cl, 2 atoms, pretty straightforward. Whereas if it's silver and plus 2 chlorine molecules, that's 3 molecules that have to come together in proper orientation. So it's a little more difficult. Okay. And final one, nature of the reactants, is the phase. So the order of increasing reactivity or speed of the reaction is aqueous is the fastest because they can get the closest together. Then it's gas, and then it's liquid, although these last two, liquids and solids, are kind of, we don't really focus too much on those. It's aqueous and gas. Aqueous is always the fastest, then gas. All right, the final thing that can increase the reaction rate is catalysts. So if you remember, catalyst, they lower the activation energy. So you have your curve, there's your reaction curve, that's the uncatalyzed. The catalyzed reaction, you start at the same place, you end at the same place, except you know, lower activation energy. Now that lower activation energy could be a single bump like that, or you could increase the number of steps, but each step has a lower activation energy. So overall, the reaction will be faster. And remember, a catalyst is something that you add at the beginning and you get back at the end. At the start, and you get back at the end of the reaction. Whereas a reaction intermediate, if you remember, a reaction intermediate shows up in the middle of the reaction and then disappears and then is used up in a following step or consumed in a following step. And just so you can see that, if you look here in this reaction here, these are from your notes. The I minus is added at the beginning, and then it disappears, gets used, and then right at the end pops back out. Whereas the OI minus is not part of the reaction at the beginning, shows up in the second after the first step, and then gets consumed again in the third step or the second step and disappears. All right, so that's a reaction intermediate, whereas a catalyst you add and then you get back. All right, so let's talk a little bit about potential energy diagrams. Oh, collision theory. Sorry, do collision theory first. So two things for collision theory: to have a proper collision so that you actually have a reaction. You need proper geometry. And you have to have enough kinetic energy. All right. If you have those two things, that's why increasing the temperature, increasing the concentration of the reactants gives you more collisions, which increases the probability of having a successful collision. Okay. And if you remember enough kinetic energy, if we remember this diagram, which has number of molecules here, and this is kinetic energy, and this we will call, this is the threshold energy. If you pass that, then you have enough energy to have a successful collision. At the lower temperature, the curve sort of looks like this. Most of the molecules are over here with not enough kinetic energy. When you increase the temperature, you get more the distribution changes, and you get more molecules over here that have enough kinetic energy to react. That's why the reaction is faster. So the blue is the higher temp. You have more molecules pass the threshold, so they're able to react. Okay. And then the last thing is potential energy diagrams, which I think everybody's done a lot of. So two types. This is your potential energy. We have this, which is an endothermic reaction. You start low and high. Remember this height here is your activation energy. That's the hump you got to get over. This difference here is your delta H. So remember, delta H is potential energy final minus potential energy initial. Final minus PE initial. So if it's positive, higher potential energy minus a lower, you have an endothermic reaction. Delta H is equal to positive. All right, and this is, I guess, time down here. And potential or endothermic reactions absorb energy, and then exothermic reactions, you start at a higher and you end lower. You still have the activation energy there. Your delta H is difference between the start and the final. And this is an exothermic. Remember, because delta H is final minus initial, it's low minus a higher number. We get a delta H that is negative for exothermic. They release energy. These are your explosions. And remember, at the peak here for both of these, this is the activated complex, which is highly unstable, doesn't sit around for very long, and then degrades into the products. So, and remember, final thing is a catalyst for both of them, like I talked about before, just lowers the activation energy you have to get over. And it might do that by multiple steps like this. Could add 3 different steps here like this, but all of them are lower than the original activation energy. So that's why the reaction speeds up. Catalyst. But the start and the end are the same. Okay. You don't change that. Okay. I posted reviews for each section in the classroom. You can now try working through the rates review, and I'll outline the other stuff in class, and I shall see you tomorrow. Have a good day, peoples.